Hey, and welcome to the second episode of this NVIDIA Industrial Engineering live stream. So I'm Neil Ashton. I'm a distinguished engineer here at NVIDIA, based just outside of Oxford. And we're going to talk today about AI physics, a deep dive into AI physics. But if this is the first time you've seen it, this whole live stream is to bring to you more information about what NVIDIA is doing in the engineering space when it comes to computational fluid dynamics, finite element analysis, whether you're in the automotive sector, in aerospace, in rocket design. We're going to try and cover the topics that hopefully can help you. In the first episode, which you can watch on demand, we'll put some links later, we did a general overview, about the vision that NVIDIA has for GPU accelerated codes, for AI physics, surrogates, and digital twins. And we said that this episode would be the deep dive into AI physics. So be prepared, and I'm sure this is where attendance is going to drop, for some code sharing and technical detail about neural networks and machine learning for engineering. But let's maybe set the scene. And hello, everyone. It's good. Yeah, it's nice to see people put in the chat. It's good to see people from around the world. If you're also from the UK, chime in. I want to see how many people are from San Diego. Okay, yeah, that's nicer than the UK right now. So maybe what we can do is let's set the scene. Why we're going to deep dive into AI physics with that real-time digital twin that I showed in the first episode. So Zach, if you maybe show my screen, I just want to briefly remind why we're deep diving into this thing here today. So basically what we showed last week was this idea that we want people to be able to do more like real-time analysis. If you're doing like a design review, you're in a car company, let's say, and you're trying to look at different designs and you want to go, I wonder what if we change the spoiler, or if we change the mirror, what's going to happen? What we show in here, and hopefully you can see it changing, is I flick the spoiler on, off. I'm doing a real-time prediction, and I'm visualizing it through the Omniverse APIs. And you can go to this website and you could actually try it yourself. But I guess the magic behind this is the AI physics, the surrogate model that has been trained on prior data and is able to give you that prediction. And I showed it last time, I'm showing you now, but we really want to get in the detail of explain what actually is going on with this. So to help me, I have brought along Rishi, who is our AI physics expert, and hopefully can demystify some of this stuff and can actually help us to understand it. Hey Rishi, how's it going? Oh, do I have to do the terrible "you're muted"? It wouldn't be an event unless I didn't have to tell someone that they're muted. So I think, yeah, if you unmute yourself, then we can hopefully carry on, or maybe I can actually do it. Oh, yeah, you still need to unmute, it says. While I let you figure that out. Yeah, what we're going to do, we're going to go through a couple of things. There you go.
Yeah, I'm here. Yep.
Okay, perfect. So, Rishi, where should we begin? I thought that maybe we could share your screen and talk about AI physics and get into some of the different architectures and different applications. So I don't know, Zach, do you want to maybe share Rishi's screen? There we go.
Yes, sounds about right. So is my screen coming through? So we've put together a couple of slides. Just giving an overview on what the nice demo that Neil showed early on, where you are seeing actual real-time inferencing, so real-time prediction of these high-fidelity solution fields, and then real-time visualization. Now, as Neil mentioned earlier, the real-time inferencing was enabled because of AI physics or surrogate models that are developed with AI physics. Now, traditionally, so we have a slide put together here showing the different methods of modeling, right? So traditionally, we are used to modeling physics where we are solving these partial differential equations. We use different models, empirical models, to model turbulence, materials, maybe transition and flow fields, and so on. And then we are solving these partial differential equations to solve PDEs. The caveat there is it's a highly tedious, complicated, and very expensive process. So enabling these real-time digital twins, as you saw previously, it's intractable when if you're doing it by these traditional solver methods. So more recently, there has been a lot of development in being able to train these high fidelity surrogate models. So as you're running these solvers, you are running these solvers over your design space. You're actually generating data. So you're generating data of the order of where you are, say, varying geometries and calculating the corresponding solution fields to those geometries. So recently, with the development in the AI-based surrogate models, we are actually able to train these models, or models which are basically parameters of a very complicated mathematical equation. So we are able to train these parameters using this data, right? And then these models, they serve as AI surrogates. So the real-time digital twin that you saw earlier was using one such model, which was trained on this massive database for external aerodynamics generated using solvers. Now, there are a couple of ways of training these models. One is a data-driven approach where you're training the parameters of the model using data. The other is a physics-driven approach where all the data that we generate using our solvers, they have a basis in physics. So there are ways of embedding that physics into your models. Now, here I've listed down a few methods of training both these data-driven and physics-driven models based on the data structures here, or the data structure you're dealing with. So, for example, if you're dealing with a graph, right? So you're running a solver, solving on a mesh. So there are models that utilize this inherent benefits of meshes, and then uses these properties to train mesh-based models such as mesh graph nets. There are models such as neural operators. So one neural operator listed here is Domino, that uses point cloud data, right? So it does not require the mesh connectivity to learn, or does not require the mesh at all to learn. Finally, on the far right, I have these transformer methods, which utilize some of the knowledge we've gained in the LLM space and brings it to the CAE space, where we train these point cloud or graph-based methods, but with self-attention, so that we can learn these representations of geometry and solution fields better. So all in all, these models, once they are trained on this data set, as we show on the bottom, they have the potential to become foundation models, and then these foundation models can be used in real-time digital twins to do design exploration, to get real-time feedback, to basically accelerate your design cycles.
What do you think? I mean, it's one of the things that I often got asked, and maybe, by the way, you can go full screen if you can on that. I don't know if it's going to work or not. But yeah,
let's see. Okay.
Is like the whole pins argument. I remember, when things were looked at maybe earlier on, 5 years ago or more, and especially coming from a CAE world for computational fluid dynamics, it sort of made sense that you could really be based on the physics. And it almost felt like that was the route to success. But then it seemed to switch, or I don't know about me, but it seemed like the mesh graph nets out of Google was like quite a turning point. Did you feel that way, that the community shifted a little bit from the pure physics driven, like pins type approaches, to the data driven?
Yeah, there was definitely that shift, because the thought process there was that the research that went into developing these model architectures had advanced to the point that the assumption was that these models were able to learn or recover the physics from the data itself, right? So they were able to learn whatever is necessary from the data and produce or predict physically consistent fields. So from that standpoint, that was a switch that we saw happening. But nonetheless, pins and physics-informed machine learning, it still has a place, right? Because no matter how we look at it, there is a scarcity of data, right? So in an ideal world where you had hundreds of thousands or millions of data sets like we have in the LLM space, for example, you could probably rely on these data-driven models and train a model which was giving you physically consistent solutions. But we don't have that. And the other aspect, like I mentioned earlier, is that most of our data has a basis in physics, right? So we are solving partial differential equations. We are modeling using empirical models, using constrained equations, material models, and so on. So this is knowledge that we have for free, along with the data that we have. So what I see today is that a lot of the community is gravitating towards obviously focusing on that data-driven approach, but then figuring out ways of using this physical knowledge into the system. So training these hybrid models where you have some data and then you have some physical bases that are used together to train hopefully a more robust and a more accurate model.
Yeah. So, we promised that we would get into some code, and so I'm wondering, in the interest of time, whether we should get into that. We did have a slide talking about PhysicsNeMo, but maybe we can just jump straight into the code of PhysicsNeMo and get going.
Yeah, sounds good. I could do a minute on just to set a drawback. So basically, everything that you see here, it can be overwhelming, right? So you have these different architectures, different ways of training these architectures. So at NVIDIA, we came up with a framework, an AI physics framework called PhysicsNeMo. And to explain this in one line is, it's a framework which contains all the tools, functionalities, model architectures, everything that is necessary for you to be able to train an AI model. So build an AI model, train that AI model, and deploy that AI model for your applications, right? For your physics applications. Now, as promised, we'll jump into the code. So PhysicsNeMo is, like I said, it's an AI physics framework. It's basically this GitHub repo, right? So let me zoom in a little bit. Now, if you look at this repo, it basically has a few core bits, right? So it has a distributed pipeline. You are training data for physics, right? Industry scale applications. You are modeling meshes with hundreds of millions of elements, right? So we provide an out-of-the-box way of distributing these training recipes, the ability to train models across GPUs. We provide a zoo of model architectures, data pipes. So especially when it comes to CAE, because you're generating data with solvers and then making them ready to be learned by machine learning. So we provide these data pipes to enable that. And a lot of utilities, metrics to calculate different, to validate and verify your models, and so on. So if you look at the core of PhysicsNeMo, it's this collection, right? A collection of utilities, models, and so on. So one other thing that we do with PhysicsNeMo is we provide a bunch of examples, reference examples, which essentially show you how to take these utilities, functionalities, put them together, and then build your end application, right? So PhysicsNeMo is not an end application. It's not going to provide you with that one-click solution. So for a different number of use cases, we provide these reference workflows. So for example, one reference workflow that we're going to look at today is external aerodynamics, and with the domino model, so the neural operator that I talked about earlier. So all the reference examples that come in PhysicsNeMo, reference workflows, they come with a nice README, and they are all reproducible to the best extent, right? So the README provides all the details, all the prerequisites that you need to install, the dependencies, and how do you basically run a basic configuration of this model. So where do you get your data set from, and so on. So this is the example that we are going to look at today. So this example is being trained on the driver ML dataset. Neil is one of the co-authors of the driver ML dataset, and it's an open source dataset available on Hugging Face. And this dataset was generated with the OpenFOAM solver. So the first step in training this model, like I said earlier, is to be able to take these raw files, raw OpenFOAM files, and convert them into a format which an ML model can ingest and train and so on. So in order to do that in PhysicsNeMo, we've come up with a sub-module of PhysicsNeMo called curator, right? So it's basically useful for curating your data. So converting your data from a solver format to a format such as serializable formats such as ZAR or NumPy, so that your models can use these files, read these files efficiently. Other than that, this curator, it provides different utilities, such as the ability to filter data, the ability to non-dimensionalize your PDEs, and so on. So today what I've done is I've taken the raw data set and I've already curated it for us. I've already curated it for us in the ZAR format. And now I'm going to go and look at some code.
And can I just say, Rashid, like,
yeah.
I feel like this is probably the value of the PhysicsNeMo is that in theory, you could do this all in PyTorch, right? It's built on top of PyTorch, but to do all of that stuff, to convert the formats, to do it in a quick way, like the model architecture in a way it's an important bit, but it's not the bit that's made. And anybody who's a developer watching this probably knows what we're talking about, like getting files, formats, processing, converting, and doing that, which isn't like bottlenecking your process, is a big thing. So yeah, sorry to interrupt you, but I feel like that is
definitely. I mean, that's an important point, because model architecture is one thing, but a lot goes into training that architecture, deploying that architecture, training it at scale, and so on. So that is where PhysicsNeMo, the actual value of PhysicsNeMo comes in. So here what I've done is I've already cloned the PhysicsNeMo repo, right? So I've cloned this repo. On one of our clusters, I already have some compute for us. So the first step we do is we basically install. So installation of dependencies is very easy. So you just do a pip install dot. It's going to grab everything that you need, all the dependencies and all the packages that come with PhysicsNeMo, and it's going to install it into your environment. The next thing we basically do, we are already into PhysicsNeMo, we want to run the external aerodynamics example. So I'm basically going to navigate to that directory. So what we want to run is Domino, and on the drive air ML dataset. So all the recipes, all the reference workflows and examples that I showed you, they are all configurable. So they come with these nicely written config.yaml files. So the config.yaml file, I've opened it here for Domino. Here you can specify your project name. So project and name, here is where all your artifacts will be archived, right? Such as model, weights, scaling factors, everything that you need to run this model. The next thing that we see here is what variables you're modeling. So this is external aero. So we have a specific set of variable and variable names, but this is again configurable. So if you're modeling a different use case, have different variable names, you can specify them here, global parameters and so on. Now, the first thing we do is, because we have already processed the data into ZAR format, and I'll show you what that looks like, we specify the input directories. So this is the directory where my training data is. If I quickly navigate to this, you'll see how the data is structured. So basically, it's these bunch of ZAR files and with IDs, right? So run 104 means the 104th sample. Similarly, run 479 means the 479 sample. So we've organized so when you run the curator, it's going to do all of that for you. It's going to organize the data for you basically in that format. So specifying these, now the next thing we do is, let's say we run another experiment, we calculate the scaling factors. So basically in the source code, we provide scripts to calculate statistics and scaling factors. So typically in machine learning, your data sets because they fall onto different scales, they are either normalized or standardized so that they fall on the same scale and are weighed equally when the learning happens. So here I've just kicked off the scaling factor calculation. What it's basically going to do is it's going to create this outputs directory, right? So under the domino, which is inside our example, creates this output directory. And under the scaling factors, it's basically going to create a file. So it's going to show you the summary of your volume fields, what the mean, standard deviation, minimum, maximum are. And then through the config file, you're able to basically set up what scaling you are going to use. So for example, in this case, we are using a min-max scaling. The next thing we do is we run the training script, right? So the training script is already written out here, and it runs the domino training script. So what the training script does is it calls your config.yaml, reads all the configs from there. What we are going to do is we are going to run the hybrid training. So we are going to train on data plus physics. And the way we specify physics is through this. So we have inside the PhysicsNeMo framework, you also have the ability to specify different partial differential equations, their formulations. You have different ways of calculating gradients, Laplacians, first derivatives, higher order derivatives, and so on. So here we specify the Navier-Stokes equation. We read the scaling factors. We set up the data pipes. So reading these R files.
Actually, Rishi, I should just point out that that's exactly your point. And some people are asking in the question about like physics-driven versus data-driven. That's exactly what you've been trying to do, right? Add the ability to bring some of this physics losses into what was classically a data-driven model.
That's right. That's absolutely right. And this example is essentially showing how you could do that, right? Obviously, there are details to it, such as what PD you're solving, for example, and so on. So those are some things you as a user having knowledge of your application brings in. So I just kicked off the training script. What the training script does is it, let me go to train_epoch, right? So that's one of the functions here. So it loops over your data set. So it loops over your data loader. So data loader will read the ZAR file, process it, and the process ZAR file is basically passed through the model to predict volume, predict surface. A cost function is calculated, so a loss is calculated. And then that loss is used to update the weights of the model. So this is the step where you calculate basically all your adjoints with respect to the weights and then update the weights of the model. And then this process goes on. So if I bring this up and show you how it looks like, so these are some of the logs that the training is printing. So it's here batch means a sample. So when it's processing batch 42, it's reading sample 42 from the ZAR files. Here what I'm showing is what is the volume loss. So volume loss meaning it's predicting volume fields that you specify here in the config file. So velocity, pressure, turbulent viscosity, and what's the loss, MSE, mean square error on those with respect to the data. Similarly, it does that for surface, right? And additionally, because this is physics-based training, we specify the incompressible Navier-Stokes, we are also calculating the continuity, momentum, XYZ, and also minimizing those. So we want our trained model to be physically consistent. So once the model is trained, it's going to predict solution fields that satisfy continuity, momentum, and the momentum equations. And this is essentially what is happening here. So when you hit training, it's going to run through your data set and then keep training the model until it reaches some level of convergence. And that could be tracked by, so again, if you go into outputs and you look at your artifacts, it creates a tensor board, right? So you can look at these. These are basically statistics showing how your loss goes with time, goes with iterations, and so on. So you can use that to govern the convergence of your model and so on. And then if you go to models, it's going to show you the checkpoint that it's going to write at different intervals. So checkpoint 00 means the checkpoint at the first epoch. You run 100 epochs, it's going to run 100 of those checkpoints. maybe a best model based on the best validation loss, best test loss, and so on. So PhysicsNeMo gives you all of this flexibility where you can take all the utilities, put them together, and then build your own application, right, for your own use case, for your specific use case. And then do a bunch of iterations, do a bunch of experiments to find which model fits the best, which training recipe fits the best, and so on.
And then what about the inference side? How would you do the...
Yeah, that's a great point. So all the recipes, they do come with a train script and then a test script, right? So what this test script, the domino testing script, is set up to do is it's basically going to read your, so the original files came in the original solver for raw solver formats, VTP, VTU, STL. So this test script is going to read your original data file. So it's going to loop over all the data files that you have that you want to test on, read the STL, VTP, and VTU meshes. It's going to load the checkpoint. So here it's where it directly picks up the checkpoint, and everything that you want to do that you are doing, you can specify in the config file. So this is the checkpoint you want to pick. This is the path where your test files are. So the VTP, VTU, STL, and this is where you want to save all those files. So once you run this test script, it's going to read these files, process them, evaluate them, and then write it back to these files. So the reason we've done it that way is so that you can use the exported files for validation and verification. So you can either open these files in your favorite post-processing tool, such as Omniverse or Paraview, or we've also provided a way of doing a more rigorous and a more consistent benchmarking. So let's say you've trained the model, you've generated a bunch of these VTP, VTU files. Recently, we've put together this submodule of PhysicsNeMo called PhysicsNeMo CFD, where one of the workflows allows benchmarking of these models. So benchmarking would be from a very CFD and CAE specific standpoint. So it would have not just the mean squared error losses and these global trends, but we also plot, let's say, let me just go to the paper, right? So we have a paper associated to this. So what it will do is it'll plot these higher order metrics, right? So obviously you have these L2 errors, mean square errors for the different models that you've done training on and that you've done testing on. It gives you a drag force correlation, a lift force correlation, Spearman coefficients, and so on. It goes further to basically plot some of the line plots. So here is line plot from one of the domino train models on the surface. So we picked the top surface of the car. This is all automated in the workflow. We'll extract that top surface. Plot
really
the
useful.
results.
Handy to test lots of different things out.
Definitely. And it's line plots, surface plots, trends, plots in the wake. So let's say you want to analyze, here we are analyzing the wake on the wheel, right? Rear wheel. And we are plotting those and comparing against ground truth. So this just gives you a consistent way and a transparent way of comparing your model to ground truth and also other models, right? So that was the idea here. Yeah.
So we're unfortunately we are running up to time, as I suspected we would do. When Rishi and I were talking about this before, I was like, I know we're going to go long on this one. I this is definitely going to be one of those ones where, I'm torn because I know there's questions here, but I know
but I hope it was useful. I hope it was useful.
We'll answer some of them afterwards. So maybe Zach, if you just go back to my screen, because I'm just going to show you a couple of links for people to essentially get going with this. So one of the things that I wanted to show is there is a DLI, Deep Learning Institute course that is all about this, accelerating CA with AI physics technology. It's a step-by-step of exactly how you do the data processing, the architecture, the deployment, training it, and then the visualization with digital twin with Omniverse. Basically, if you go to that page, you're going to be able to go through in your own time because Rishi just went through this and we tried to go through in 20 minutes. So we'll put these links up as well so people can do it. Oh, it's there. We'll put it into the chat. So I'd highly recommend to do that. That is really going to be your step-by-step guide. And also there is, if you go to the GitHub page, there's discussion. So if I go like here, you can go, not only can you download the code, but you can file issues. You can have like discussions on any things questions you have on the code. But again, doing the DLI course, I think will set you a really good foundation for all of this. So Rishi, I want to thank you very much for taking the time to do this. I hope that people enjoyed this. We're gonna listen to you. So if you want more episodes like this, you want to go a deep dive into AI physics, then we could do an episode 2A that can go in this. And we'll be back for the next episode in a couple of weeks' time. So please tune in. But for now, thank you very much for joining, and hope you have the rest of a nice day wherever you are in the world.
Great.
Thanks, Rishi.
Yeah, thanks for having me, Neil. Thanks, everyone.